Hello everyone, welcome to Chat with an Astronomer. Today with a special episode because today I'm not talking to a PhD researcher at the IMPRS, but actually to a supervisor. Today I'm glad to be talking to Professor Anton Zensus. He's a director at the Max Planck Institute for Radio Astronomy here in Bonn. He has supervised a lot of PhD students and he's also the speaker of the Max Planck Research School. He works on very long baseline interferometry, which means that he's one of the people who's able to actually photograph black holes, which is something that we'll talk about in a second. And he can also give a lot of information on on what qualifications a PhD student needs to bring with them. And it's also something that we will talk about today. So thank you very much for being here, Professor Zensus.
Thank you for this opportunity to speak with you today.
So, what exactly is your research topic?
I'm leading the scientific division for very long baseline interferometry and radio astronomy here at the Institute. And so long baseline interferometry, high resolution astronomy is the core business of what I do with my researchers here.
So your topic sounds very fascinating. Maybe you could explain shortly, what is the big research question that you are looking for in your work?
So what we have in the universe is galaxies, and in particular there's a large number of so-called active galaxies at cosmological distances in many cases in the universe, which are far away and very, very luminous. They emit an enormous amount of power, and it is the source of their properties. It is the physics of these objects that I've been studying for many years. So active galactic nuclei, and in particular, imaging the central regions so we can understand what's going on at the central locations where we suspect that they are massive, supermassive black holes of millions of billions, up to billions of times the mass of the sun, so that we suspect there are black holes at the center of these active nuclei, and there are large jets of matter and radiation emanating from these central regions that we can observe with radio astronomical techniques. So the large picture is that we do imaging observations to understand the physics of active galactic nuclei, and we do this with a host of radio telescopes and different methods, and of course also theoretical work.
So it's fascinating that you actually study the center of active galaxies and the supermassive black holes there. And as far as I understood, you were also involved in the first ever image taken of a black hole?
That's correct. This is the galaxy M87, some 55 million light years away from Earth. And this, together with a few other sources, one in particular, that's the center of our own galaxy, was one of the prime candidates to find or confirm the existence of a supermassive black hole by direct imaging. For many years, we have been pursuing improving the method of VLBI, very long baseline interferometry, to get better and better angular resolution, imaging fidelity, if you like. And in 2017, we did experiments on the center of our own galaxy, but also the center of the galaxy M87, to try to make an image at a wavelength of 1 millimeter of the region on the dimension of what we expected would be the size of the accretion disk around the black hole. We have a precision in our imaging that would allow us to read a newspaper here in Bonn that somebody holds up in New York City. That kind of image fidelity and angular resolution is possible with this method. And we applied the method to M87, and we made an image of the structure in the central region that is exactly like to what the expectations for a black hole structure would be. And so for the first time ever, we made an image of event horizon scale structure in the radio, and we believe that we confirm the existence of supermassive black holes with this, and actually showed for the first time an image of the structure around that non-radiating region of the center of the black hole.
So if someone wants to do research in your field and wants to actually pursue a PhD there, What kind of qualifications do you think are most important?
So I would say there's two types of work related to this science. One is experimental type. There's a whole range of experiments that are done. This is a golden age in the study of black holes, if you like, because we have gravitational waves that give hints about the existence of black holes. We have infrared observations of stars around the center of our own galaxy that again give very good insight in the properties of the black hole at the center of this galaxy. And we have this method in the radio where we can direct image black holes. So an experimental astronomer has many opportunities, and there's many more areas, like the high energy areas that you can work in. So a recent master's graduate who wants to work in this field for a PhD would actually join one of the teams, like my own group here in Bonn, that actively works with the data, generates new data, does observing with the Effensberg radio telescope here and other radio observatories at millimeter wavelengths in particular. So as a person, a PhD student wanting to work with us on experimental work would be interested and would have some experience in experimental radio astronomy. And then there's theoretical work, both numerical and analytical work. So somebody more interested in the astrophysics of this would join a professor or a group that focuses on the theoretical work in this area and would come with a strong background in theoretical physics and mathematics, of course. So these are the two main types of work. There's also some people with more of an engineering focus and development focus on them. So somebody is interested in doing hardware and building radio receivers or working on digital equipment, for example, also would find it very good. So these three types of skills have previously, we have previous students who had those particular skills and did very well in their work.
And are there any tips or any advice that you would give someone who's currently doing their PhD in astronomy or any other field for that matter?
I've learned, I did this myself many years ago, so I think the being involved in active research in a very hot topic has a lot of opportunity, but also carries a lot of risk in the sense that in our case, the Event Horizon Telescope, the EHT project that did this first image of the black hole, is a collaboration of many hundreds of people around the world. So that is both good and not so good or difficult because you are working with many people, but you're also depending on many people. So my advice would be to make sure in your thesis plan that you work out with your scientific advisor and your professor that you have something like a plan A, which is the ambitious project participating, say, in finding the next black hole image, but at the same time you have a more secure second project that allows you to finish in the time that you have given yourself towards the completion of your thesis. I would also normally say that it is good to get exposed early to scientific writing and presentation, in particular presentation at conferences. So now currently because of the Corona period, we can't go to scientific conferences, probably won't for a while. And so my advice is to make sure that through whatever channels possible, like this format or other group meetings, that you do train, that students in our field do train presentation, interaction, discussion, discourse with other scientists.
Yeah, that's very helpful indeed. And I think for every student, it takes a bit of courage to actually go to a conference, but in the end, it's really rewarding. And finally, one closing question. What is something that has surprised you in academia or in your research that you would like to share?
I was stunned by the success that we had ultimately after working in this field for almost 40 years. I was stunned by the high point we had when everything came together, all the observing conditions, all the technology, all the skills, all the methods and imaging and calibration came together, and we were able to make an image of a black hole. So it truly was a breakthrough, and it was a surprise that in my time as a director that we would have this, because normally science takes a long course, and only rarely do you really make a big surprise or surprisingly big discovery, which we were able to. That was certainly in recent years the biggest surprise. But I have to say, this is unique, and so I will give you a second example, and that is being able over the last couple of decades to improve astronomical instrumentation around the world and in space to a level that today we can gain data, we can gain insight about phenomena in the universe that some tens of years ago we wouldn't have dreamt of being able to do. That truly was an achievement and a surprise that it has worked so well. And this is for many, many areas. Again and again, I think astronomy is one of the examples of a science where people collaborate in the world. And that is, in these days where there's a lot of division in the world, still a sign for that, at least for a period of time, working in astronomy is a worthwhile endeavor.
Yeah, thank you very much. That's a very hopeful note. I fully agree. Astronomy is a worthwhile endeavor. So yeah, thank you very much for this conversation, and yeah, have a nice day.
Thank you, and wish you well.